The basic idea behind this talk is that I want to help focus your attention on what drives success in machine learning. I understand a lot of people at this conference are just beginning their journey of learning how to work in AI and how to use machine learning. The thing is, a lot of tutorials and textbooks and videos about machine learning don't really focus you on exactly what will lead to the fastest improvement in your ability to function in the field. Most tutorials that you read proceed by amassing several different algorithms, inductive principles, inference techniques, and so on. They make it seem like the way to become an expert in machine learning is to know exactly how every algorithm from the relevance vector machine to Bayesian linear regression works. So I'd say over here, this is one of the things that people seem to think drives success in machine learning. It's always nice to know about more algorithms, but I would argue it's far more important to have lots of data and to know how to apply 3 to 4 standard techniques. When I say know how to apply, I mean to know how to configure their settings, understand whether they're working well or working poorly, and understand how to adjust and react if you find that they are working poorly. So this talk today focuses on this third topic, how to apply the bread and butter techniques of machine learning. As a case study that I'll use as a running example to help give you concrete instances of the different advice that I apply, I'll be telling you about a system that I helped build at Google. This is the Street View address number transcription system. The basic idea is that Google Maps can give you directions to many different buildings and addresses around the world, but we don't necessarily have all the buildings you might want to go to in our maps already. One way that we can add more buildings to our maps is to use the GPS and photo data from the Street View cars. As the Street View cars drive around different streets, they take photos of everything they see, and they also record the GPS coordinates of their location when they took the photo. So if we see the address number of a building and that building isn't already on our map, we could, in principle, put that building into Google Maps at the correct GPS coordinates. The problem is there are an awful lot of address numbers that we take photos of, and it's labor intensive to transcribe them and put them on the map. The way we solved this problem was we built a neural network to transcribe the numbers out of the photographs and convert them into a computer-readable digital format so that we could then update the maps entries. Throughout this talk, I'll refer to a few different challenges that we encountered along the progress of this project, and I'll describe the way that we overcame each of these challenges as part of my general advice for you to apply in your own work. The basic methodology I'm going to advocate is a 3-step process. In the first step, you identify the needs that you have for the product or the service or the research project that you're building. You then use these needs to figure out what your goals should be. Your goals should be specific and quantitative. Part of the planning process is to choose what metrics you will use to measure success and exactly what kind of numbers you need to achieve for those metrics. After you've set up your goals, you need to build an end-to-end system as soon as possible. You don't want to over-engineer your project before you begin working on it. Just think of the simplest thing that can actually produce a usable output for the task that you want to solve. It doesn't matter if the output is actually any good or not. It just needs to be something that can actually be scored using your metrics. Once you have the end-to-end system in place, you begin step 3, data-driven refinement. In step 3, you measure different properties of your system. You figure out which aspects of it are working well and which aspects are working poorly. And you use these data-driven metrics to improve the parts that are working poorly and improve them. After you have improved your system with this data-driven refinement process, you might end up with something that's complex at the end, but it won't be over-engineered. It will be engineered to be just as complex as you need to solve the task. If you design a complicated system before you've actually started tackling the problem, you might overestimate how complicated it needs to be and end up with something that's harder to maintain and use in your business than you need. All right, so that's the overall 3-step process. Now I'll go through each of these steps in a little bit more detail. The first step is identifying the needs of your product or service and defining metric-based goals that will ensure you meet those needs. One thing you need to think about is how much accuracy you actually need in your product. Obviously, everyone would always like to build a machine learning system that's absolutely perfect, but that's usually going to be extremely expensive, if it's even possible at all. So you need to think about how much time and money you're going to invest to get different levels of accuracy. And you probably want to initially plan for the lowest amount of accuracy that's actually usable in your application. Some applications intrinsically demand lots and lots of accuracy. If you're building a surgery robot that's going to cut apart people's veins and stitch them back together, any machine learning you need in there needs to be extremely accurate. Otherwise, you're going to cause lots of pain and suffering and injury. But if you're building a mobile app where you take a picture of your friends and it says which celebrity they look like, there's not even really a right answer in that case. So it's all right if you don't necessarily have the most accurate machine learning system of all time. Most applications fall somewhere in the middle. A lot of business applications where you use predictions to plan investments and sales and acquisitions and so on. They fall into this realm where if you can make better predictions than the humans are already making, you'll make money. You'll at least save money relative to what you do if you operated off of the human predictions. And the more accurate your predictions are, the better you'll do. But just getting past the human baseline is sufficient to have a useful product. For the Street View address number transcription system, we determined that we wanted to have human-level accuracy in our transcription. We wanted to make sure that we weren't getting any address numbers wrong compared to what human transcribers would get. The reason is that it's very frustrating if you ask for directions and then Google Maps leads you to the wrong address. So we needed to make sure that we didn't reduce the accuracy below the system that we were already using. In order to measure the accuracy, we were able to just use the percentage of examples that are correct. That's a relatively straightforward metric. But there's other tasks where you don't want to just measure the number of examples that are correct. For example, if you're building a test to determine whether someone has a rare disease, you can just say, nobody has the disease. And because the disease is rare, you'll get a very high accuracy that way. Suppose that only 0.1% of all people in the population have this disease. You'd get 99.9% accuracy. For cases like that, there are other metrics that you should use. So precision tells you the number of detections that are correct. In the test for the disease, if you say someone has a disease, precision is the probability that you're correct that they actually have the disease. Another metric is recall, the percentage of positive examples that you actually detect. So in the disease example, this would mean of all the people who have the disease, what percentage of them do you correctly diagnose as having it? For the Street View application, this didn't actually matter because our different classes that we were categorizing into were the 6-digit numbers that addresses can take on. There's not any one class that's extremely rare and another class that's extremely common. One metric we did end up using that was important, though, and that you don't see very often and that I think should be used more often, is coverage. So you probably haven't heard of coverage before. The idea behind coverage is you can have a machine learning system that refuses to classify some inputs. Basically, if you show it an example where it's not confident what the correct answer is, it can say, I am not confident what the correct answer is. You should not use machine learning to solve this particular input. Coverage is the percentage of examples that the machine learning system actually confidently classifies. And using this metric was key to our success on the Street View house number pipeline. It's very difficult to reach human-level accuracy on address number transcription if you insist that the network classifies every single example that you show it. But you can easily reach human-level accuracy if you're willing to reduce coverage. If you're willing to say, I'm going to throw out 6% of the examples so that I can reach 99.5% accuracy on the remaining ones, then you can actually get as high of accuracy as you want, provided that you're willing to throw out more and more examples. So when we set our goals for the Street View house number transcription pipeline, we set our goals in terms of accuracy and coverage. We wanted to get human-level accuracy at a specific level of coverage that we felt was necessary to justify the investment in the machine learning pipeline. There are other applications besides classification out there. For example, if you're using regression, you need to use a metric based on the size of the prediction errors that you make, like mean squared error or mean absolute error. All right, so the second stage of the methodology is where you actually build your end-to-end system. You want to get your system up and running as soon as possible so that you can identify what the real challenges are. A lot of the time, the aspects that are challenging are not the ones that you thought they would be before you started building everything. And so you want to find out what's actually going to be difficult as soon as possible. I'm advocating building the simplest viable system first. The question is, what's the simplest viable system? And where should you start? What should you use as your beginning point from which you start to iterate? One thing that you can do if you're working on an application that's already been done before by other people is just to find a published result in this same field and copy the state-of-the-art method. You might not want to use literally the method that gets the absolute best accuracy. You might want to get a simple and easy to implement one that's very close to the best accuracy. If you don't know of any existing publications that solve the same application as you, then you probably need to make a judgment call about what a relatively standard algorithm is that you should start with. So now I'm going to give you some guidance about what some reasonable baselines are to begin with. One of the first questions to ask today in 2015 is whether you should use deep learning or not. Deep learning is very hot right now, and it's my specialty, so you're probably expecting me to tell you you should always use deep learning all the time. That's actually not the case. One of the first things you should decide is whether the problem you're tackling requires deep learning or not. Many tasks have lots of noise and very little structure in them. Usually, if this is the case, you don't want deep learning. Something like linear regression will suffice. If there's relatively little noise in your problem setup, and there's a lot of complex structure, then you can use deep learning. So when I say that something has complex structure, I mean you have a task like looking at an image or a video or a paragraph and summarizing what it means to a human being, saying, this paragraph contains positive sentiment or negative sentiment, or this photo contains an airplane. Those involve really complicated mappings from individual pixels or individual characters or individual words to very high-level abstract ideas. But if your system has a lot of noise and very little structure, and you're just saying something like, here is a house, and I'm telling you how many square feet it has, please tell me how much it costs, then there aren't very many different variables there. The relationship between them is not very complicated. You can solve that with a much simpler machine learning system. The best shallow baseline to use in one of these high noise, low structure situations is to use the system that you're most familiar with. A lot of people will debate endlessly which machine learning algorithm is the best. But there are theorems out there that actually tell you that there is no best machine learning algorithm. Usually you're going to perform the best if you use something that you're comfortable with and that you understand. If you understand logistic regression really well and you know how to tweak it, then use logistic regression. If you tweak logistic regression effectively, you will do much better than if you use an SVM and don't tweak it well. Also, the same applies in reverse. If you're familiar with support vector machines and you think you understand how to tweak those, then by all means begin with support vector machines. Before about 2013, before deep learning became really effective, boosted decision trees were one of my favorite default algorithms. If you have a good implementation of those and you feel comfortable using them, then they're a really good baseline in a lot of cases. And I successfully used those for a lot of robotics problems. Okay, so suppose that you have a very complicated problem and you have enough data to fit it. In that case, then you want to go ahead and use deep learning. So what deep learning model should you use? The basic way that you decide what kind of deep learning model to use is, well, first, as I said on the earlier slide, if there's already a published baseline that works well in this task, then just copy the architecture from the published baseline. But if you're working on a totally new problem and you need to make your own decision about what to use, the main way you decide is you look at what kind of structure there is in the data. Some data doesn't really have any structure at all. It's just a list of measurements. And you just, in this case, you could just apply a fully connected neural network to it. There's no special structure in the neural network at all. It's just completely specified matrices at every level. A lot of tasks have spatial structure to them. This is things like images or videos or data based on maps or any kind of thing where you have sensors aligned on a grid. In that case, you can use a convolutional network. A convolutional network is a kind of neural network that says it's going to apply the same little function at every different point in space. And if you learn that one little function really well, then you can apply it everywhere. You don't need to independently relearn it at every location in the grid. Finally, if you have a kind of data that has sequential structure to it, then you want to use a recurrent neural network. This is if you have something like text, where you want to read a long sentence, and then at the very end, you're going to be asked a question about it. So at the end of the sentence, you need to remember something from very early at the start of the sentence. You might notice that there's a little bit of overlap between sequential and spatial structure. You can kind of think of time and space as interchangeable. So there is a little bit of a judgment call about whether you want to use convolutional or recurrent networks. In some sense, they are similar things. In recurrent networks kind of imply that you're convolving over time. But that's maybe a little bit more advanced than I need to get into right now. you could do reasonably well with the choice of either a convolutional or a recurrent network anytime that you have this kind of structure available. Okay, so suppose you've decided that you want to use a fully connected neural network to solve some kind of unstructured data processing task. What's a good baseline for that situation? As of 2015, I would say that the best baseline to start with, the one that's really easy to implement and works well in a wide variety of settings, is the 2 to 3 hidden layer feed-forward neural network. These are also called multi-layer perceptrons. And you can go ahead and add more hidden layers later if you decide that they're needed. But to begin with, just try 2, 3, maybe even just 1 hidden layer. You definitely want to use rectified linear units as your baseline. Don't use sigmoids. Sigmoids are considered out of date now, and rectified linear units are far easier to use. You also probably want to use dropout, Geoffrey Hinton's regularization strategy, where you randomly mask out half of the units on every step of training. To train the neural network, you want to use stochastic gradient descent and momentum. This technique is really effective. It works very well as long as you have a few thousand examples per class, and it's been applied to everything from speech to vision to natural language processing. It's really the standard engine that drives pretty much everything in deep learning right now. Part of the reason I'm doing this talk and highlighting this as an example of a great baseline for right now is that it can be hard to sift through the literature and determine what the latest advice is. So a lot of people who are first getting into deep learning read that deep learning is all about deep belief networks and deep Boltzmann machines and so on, or autoencoders. I don't really recommend those methods right now. Those were performing very well from about 2006 to 2012, but they're complicated and difficult to make work. You need to understand a lot more ideas to get them to work well. And these days, there are very few tasks where they're actually the state of the art anymore. Unless you know for a fact that something like autoencoders is necessary to perform well on the application you're working on, you probably want to default to this backpropagation-based rectified linear network. So that's what you do if your data doesn't have any particular structure to it. If your data has image structure, then you want to use a convolutional network. So I also have some pretty strong recommendations for what to use if you're in the convolutional setting. If you're able to do it, I suggest using an inception network trained with batch normalization. You'll read a lot of papers out there about all these different tricks to train very deep convolutional networks. And in a lot of cases, it turns out that you can actually train as deep of a network as you want just by using this batch normalization algorithm that was released by my colleagues at Google earlier this year. Inception and batch normalization are somewhat complicated, and not every library offers these kinds of networks. So if you're using a library that doesn't support, for example, the inception network, you can fall back to a simpler convolutional network. Once again, I recommend using rectified linear units, the same as in the feed-forward network case. So just use a convolutional network with rectified linear units, regularize it with dropout, and train with stochastic gradient descent and momentum. All right, finally, if you have a task with sequential structure, then you can use a recurrent network. In this case, the standard baseline I recommend is the LSTM, developed by Sepp Hochreiter and Jürgen Schmidt-Huber. Oh yeah, I see somebody's asking about unsupervised learning. If your task really is unsupervised, like if your final goal is not to do classification, then go ahead and use an unsupervised learning algorithm. It depends which kind of unsupervised task you want to solve. If you're doing something like denoising, then use a denoising autoencoder. If you're doing something like generating new samples, then you might want to use a generative adversarial network or a variational autoencoder. Let me read the follow-up. Oh yeah, hidden Markov models. Hidden Markov models are perfectly fine as long as you don't need the hidden state variable to be complicated and high dimensional. If there's a very high dimensional hidden state, then hidden Markov models don't scale as well as recurrent nets. Okay, so popping back to the recurrent network situation. I would recommend the LSTM as the default model that people use when tackling a complicated AI-complete sequence modeling task. You can train this with stochastic gradient descent. I've heard a lot of people say that you don't even need to use momentum in this case. The LSTM already makes it easy enough to optimize that you don't need that extra step, but momentum is usually helpful. One thing that's really important when training any kind of recurrent network is to apply gradient clipping. That means that during backpropagation, as the gradient flows backward through the network, you impose some maximum size on the gradient, And if the true gradient exceeds that size, you clip it to be smaller than what the math actually says it should be. The reason for this is that when you propagate backward through several hundred steps in an LSTM, it can make the gradient become quite large, and a very large gradient can actually do a lot of damage if you take a gigantic gradient step. So just by clipping it, you can avoid that instability problem. So I see there's a question about whether Google has any new methods to parallelize LSTMs well. I don't actually know anything about the pyramid LSTM myself. So one thing is, at Google, we do train a lot of things using asynchronous gradient descent, where we just train many copies of the LSTM simultaneously. That's using our internal disbelief library. That's not really something that people outside can just grab and use. But there are other multi-replica learning strategies that have been made public. One last trick that you should probably use in your baseline for a recurrent network is setting the forget gate bias to be high. That makes it so that the forget gate of the LSTM initially says not to forget anything, and that helps to make sure that information flows through the network originally. All right, so stage 3 of this methodology pipeline is to do data-driven adaptation. After you've got your baseline in place, you choose what to do next based on data. An important thing at this step is to not believe hype about different kinds of algorithms out there. Every week, there are dozens of papers appearing in arXiv saying, we have this new, Langevin Bayesian variational variant of this algorithm you're already using, and if you use this, it's going to be 1,000,000 times better. Most of the time, most of these papers are just one author trying to get attention for their own method and try to build their resume. It takes quite a long time for an algorithm to get established and for you to really know that it's trustworthy. So filter out a bit of the noise, try to take a bit of a conservative approach to what algorithm to use, and expect most of the benefit you get from doing very bread and butter stuff, where you adapt the settings for the algorithm you're already using, or you gather more data. And when you do change from one algorithm to another, it shouldn't be just because you've read that some tool is the hottest new thing. It should be because you've used a metric to figure out what the best next step should be. The most important metrics are the training error and the test error. You measure how well you're doing on the training set, and you measure how well you're doing on the test set. If you're not doing well enough on the train set, then you're underfitting. And if you're not doing well on the test set, then you're overfitting. So I'll talk a little bit about how to address each of these problems. If you have high training error, there's a few different steps you should take. Most textbook advice will immediately start telling you how to do things to your machine learning model. But I would actually say the very first thing you should do is check whether your data has a problem. Make sure that it hasn't been collected poorly or something like that. If the data has defects, then your algorithm won't be able to fit it. Next, you should actually inspect your software for defects. And specifically, I'd say don't make your own software unless you definitely know what you're doing. Using other established software that's been tested and improved by many people is a good way of being relatively confident that your high training error doesn't come from a bug. Once you're sure that both the data and the algorithm are correctly gathered and correctly implemented, you can begin to address high training error by adapting the learning rate and adapting the other settings that affect the optimization procedure. You can also make your model bigger so that it can fit a larger training set. I'll give you a few examples of each of these things here. So for the Street View transcriber, one of the biggest things we did was we changed the way that we cropped the photos that were provided to the system. After we had built our baseline, we started looking at which examples it was getting wrong. Over here on the left, here's an example of a kind of mistake that it was making. We would see these photos that say 6624, and the correct answer is 26624. So we realized that our automatic cropping system was actually cropping a little bit too tight. We solved that just by telling it to make wider crops. And now you can actually see the complete digit, the complete address number. So this is a really simple and dumb mistake. And it's very simple to fix. It doesn't require any real knowledge of machine learning to fix. All we did was look at what mistakes were happening and try to categorize them and figure out what the largest bottleneck was. So that was our biggest change that we did in terms of how much it improved our performance, was we found that sometimes the crop was too tight and we were misclassifying examples because of the crop. Our biggest change during the development of the pipeline was not to change algorithms, introduce unsupervised learning, anything like that. It was just to measure where the mistakes were happening and make a very simple common sense change. You can also fit the training set better by increasing the size of the model. Here we have a graph of how our our performance improved as we added more layers to the Street View transcription system. This is pretty simple. We just kept adding more hidden layers and the performance kept going up. A lot of the time, if you have a lot of data, you'll find that you can keep making the model bigger and bigger, and you always see an improvement. A lot of the time, you'll end up finding that your performance is limited by the size of the model that you're able to afford to run. Okay, so that's what you do if you have high training set error. What if you have high test set error? One thing you can do is you can do data set augmentation, where you make multiple copies of your training examples transformed in different ways. That's a relatively cheap way of getting more data. You can also just pay to get more data. If you aren't using a regularization strategy like dropout already, then you can add dropout and hope that reduces your test set error. So here's a graph of what happens as you increase your training set size. On the right, I'm plotting the optimal size of the model. So as you get more and more training examples, you'll need to use larger and larger models. On the left, I'm showing a few different things that happen. One of these is the training set error at the optimal model size. Most of the time in deep learning, your optimal model is going to get 0 training error. And the question is just, how badly does it overfit? What is the gap between train and test performance? You'll see that test performance drops over time as the number of training examples increases. So a lot of the time, the size of your data set is the most important factor driving your success. So that's the end of my talk. If you'd like more information, feel free to look at the deep learning textbook that I'm writing along with Yoshua Bengio and Aaron Corville. It's online at goodfellow.github.io, and the subdirectory is dlbook.